Hi everyone, this video is going to be on DDIM. For all our prior diffusion videos, we had explicitly just worked with DDPM, but the generation process with DDPM is really slow. So this one is going to get into all aspects of DDIM, which allows us to speed up the generation process. The video will cover the following sections, and all of these are timestamped, so feel free to jump to any specific section if that is all that you are interested in. We'll start off by doing a recap of DDPM. The remaining parts of the video assumes you already know the mathematical details of DDPM. If that is not the case, then it's best that you first see my DDPM video prior to DDIM. In DDPM, we have a forward process that takes samples from original distribution and at each step adds a bit of noise and destroys a bit of the original structure. The data points could be images of certain kind, videos, music, speech, anything. But for the purpose of this video, let's just assume that we are always working with 2D images. This forward process of DDPM is Markovian. Given xt-1, xt is independent of all other previous time steps. The forward process is formulated in this manner, where the distribution at each time step is a Gaussian with predefined mean and variances. Beta underscore t was the schedule of variances, and the authors of DDPM used a linear schedule, with beta increasing linearly over time steps, and the number of time steps used was 1000. The entire forward process allows us to take samples from original distribution and convert them to samples from standard Gaussian distribution. We then tried to have a model learn to approximate the reverse distribution at each step, that is, given xt, learn to approximate xt-1. If we are able to achieve this, then we can feed our model samples from normal distribution, and at each step, the model will take a noisy image and give us a less noisy image. After repeating this for 1000 reverse time steps, we should be able to get a sample that looks as if it came from our original data distribution. With the specific formulation of forward process that we worked with in DDPM, we saw that to get to xt, rather than going from x0 to x1, x1 to x2, all the way from xt-1 to xt, we can directly get to xt from x0. The way we derived this is that we started with this expression of xt in terms of xt-1, and here we have just replaced alpha underscore t as 1 minus beta t. And epsilon t is a random variable representing samples from normal distribution. So we are using reparameterization trick to generate samples from this q of xt given xt-1 distribution. But rather than going through the entire chain, we saw that we can get to xt directly from x0 in this manner. Here alpha t bar was the cumulative product of all alphas till time step t. And epsilon is again a random variable representing samples from normal distribution. In DDPM video, we had gone through all the steps to derive this, so I won't go through that here. Now, with the goal of ensuring that our DDPM model learns to generate data as close to our training distribution as possible, we start with optimizing the log likelihood of observed data. From there, we move to this lower bound objective, which upon simplification ends up being the KL divergence between predicted reverse distribution p theta and ground truth denoising distribution, which is q of xt-1 given xt and x0 at each time step. Then using Bayes' theorem, we found that this ground truth denoising distribution ends up being a Gaussian and got an expression for it which had this mean and variance. Given that our target distribution has this form, we also ensure our predicted reverse distribution also is a Gaussian, with mean being formulated in the same manner as the ground truth mean, except instead of x0, we will have predicted x0. We also fix the variance of each time step to be same as the ground truth. Then our training objective becomes minimizing KL divergence between these two distributions, which ends up being this. So squared difference between means with different weights for each time step. Since this mean is nothing but a combination of xt and x0, this further gets simplified to squared difference between original image and predicted clean image. Furthermore, because of the formulation of forward process, we can also rewrite x0 in terms of xt and original noise added, or noise prediction. So we finally end up with squared difference between original noise and noise prediction for each time step, again weighted by a factor for each time step t. With this objective, we end up with the following training procedure. We have samples from our original data distribution, and then we iteratively train by randomly sampling from all possible time steps. For each training data point, we pick a random time step and a random noise sample. Generate xt using our forward process equation, which gives us our noisy image sample. And we then train our model to predict the original noise added. Like we had seen in DDPM, the authors ignored the weight factor for each time step and used a simpler objective, which was just MSE between noise and noise prediction, and found that to give better sample quality. During sampling of DDPM, we use our model to move from a sample xt, which is nothing but a sample from normal distribution, all the way to prediction of x0 by going through this chain of reverse steps using our predicted reverse distribution. We had this expression for the ground truth denoising distribution, which was in terms of xt and x0, and as we saw, we can rewrite it in terms of xt and noise. Similarly, the mean of our predicted reverse distribution can also be rewritten in terms of xt and noise prediction, which gives us this expression for the mean. For generating data using our trained model, we start with xt, feed it to our model to predict noise. Using the predicted noise and xt, we get to the mean of xt-1 distribution, and variance is same as the variance of ground truth. Then using reparameterization trick, we generate a sample from the predicted distribution at xt-1. Then again feed this xt-1 to our model as input, get noise prediction, and generate xt-2, and iterate over all 1000 steps to finally generate our sample. Once we trained this model on MNIST dataset, we were able to produce quality samples of digits. But while the quality of samples were high, since the inference process had to go over a sequence of 1000 steps, the generation was slow. So now with the recap done, let's see what happens in DDIM and how does it lead to faster generation. Before starting with the forward process, rather the process of generating noisy latents in DDIM, there are a couple of important points regarding the entire DDPM math that we must take note of. Our objective that we ended with for all time steps was this scale divergence term between predicted and ground truth denoising distribution. Our ground truth denoising distribution's mean was a combination of xt and x0, which using this relationship, we could rewrite to a combination of xt and noise, which ends up being simplified to this. The predicted distribution could also be formulated in the same manner, and ultimately we get to this expression for our objective. Now assume that our ground truth denoising distribution's mean is something different, but it is still a linear combination of xt and noise. So as an example, say it's 80 times xt plus bt times noise and some variance. And also assume that we somehow ensure that q of xt given x0 is same as before for all time steps. So using reparameterization trick, we can get to xt same as before from x0, even for this new distribution. How does our training objective change with these two assumptions? Well, let's go through the same set of steps. We'll formulate our predicted distribution to also be of the same form. Then again, optimization objective will involve KL divergence, which gives us the same squared difference between means, which again ends up being square difference between original noise and noise prediction. So the only thing that will be different is the weight factor for all time steps. Only these will undergo a change from our prior objective. If you ignore these weight terms, which we anyway ignored in DDPM, then everything else remains the same. So the training process and objective with this modified ground truth denoising distribution will be same as DDPM. During training, we'll again feed our model xt, which given x0 will have the same distribution as before, since we ensured q of xt given x0 is same as DDPM. The model will predict the noise with this as input and is trained using MSE between noise predicted and original noise. So that means even though we have modified the ground truth denoising distribution to be different, as long as the mean formulation is still a linear combination of xt and noise, and q of xt given x0 remains the same, the optimization objective and training process also remains the same, which means the same trained model can be used, and the only thing that we'll have to change is the sampling process, where the update from xt to xt minus 1 will now be different, and will be according to these new coefficients at and bt. By the way, the same holds true if you define mean as a linear combination of xt and x0, because after all, you can get noise using xt and x0 from this equation. So the end objective remains similar, whether it's the linear combination of xt and x0 or xt and noise. With this background knowledge, let's see the change of noisifying process from DDPM to DDIM. The DDIM paper uses a different notation than DDPM. Basically, what is referred as alpha bar, so the cumulative product of alphas in DDPM. In DDIM, it's referred as alpha. But I wanted to keep notations same as the previous DDPM video, which means every time you see an equation for DDIM in this video, they will be different from the one mentioned in the paper. In the video, that equation will have alpha bar, but in the paper, the same equation will have alpha instead of alpha bar. But they are both the same, just using different notations. Okay, in DDPM, our joint distribution of x1 to xt was factorized in this manner, with q of xt given xt minus 1 defined as a Gaussian. So to generate the entire sequence of noisy images given a clean image, we first generate x1 given x0, then x2 given x1, and so on till xt. DDPM's forward process of noisifying a clean image is a Markovian forward process. A generative model that approximates the reverse of this needs to go through the entire chain of 1000 time steps. The authors of DDIM instead define a family of distributions q sigma, where the joint distribution is factorized in this manner. So with this factorization, notice the change in how one would generate the sequence of noisy images or latents. Given a clean image x0, we first would generate xt, that is the last latent. Then given xt and x0, we generate xt minus 1. Then given xt minus 1 and x0, we generate xt minus 2, and so on. The authors formulate the mean of q sigma of xt minus 1 conditioned on xt and x0 as this, and also have q sigma of xt given x0 as this. So same as the formulation of distribution of last time step in DDPM. Earlier, we saw that as long as q of xt given x0 for all time step remains same as DDPM, and q of xt minus 1 given xt and x0 is a linear combination of xt and x0 or xt and noise, we can use the same trained DDPM model for sampling. Here the mean is specifically defined as a combination of xt and x0. So if we somehow prove that with this mean, q of xt given x0 remains same as DDPM's distribution for all time steps, then we don't need to train a different model for this diffusion process. Let's quickly see the proof of this which the authors provide in the paper, and they use induction for it. So given q sigma of xt minus 1 conditioned on xt and x0, and q sigma of xt given x0 as the base case, where t is the last time step, if we can show that if q sigma of xt given x0 is this, then q of xt minus 1 given x0 also has the same form, then we are done with the proof. because with the base case of last time step, one can just repeat this for t and t minus 1, then t minus 1 and t minus 2, and so on. The authors use the following identity for the proof, which states that if p of x and p of y given x are Gaussians of the following form, then p of y can be derived to be this. We'll use this to get an expression for q sigma of xt minus 1 given x0. So that will be our p of y. P of x is q sigma of xt given x0, which we assume to be of this form. P of y given x is q sigma of xt minus 1 given xt and x0. By matching the mean and variances, we can get values of everything involved in the formulation of p of y, or q sigma of xt minus 1 given x0. Like for example, using p of x and q sigma of xt given x0, we get mu as square root of alpha bar times x0. And similarly, these are the values of remaining terms. So once we have got the expression for all these terms, we are equipped to compute q of xt minus 1 given x0, or p of y. The mean of that would be a mu plus b, which is these two terms. And if you notice here, these two get cancelled out, and only square root of alpha bar t minus 1 times x0 remains. For variance, we have sigma square I plus these terms, and this gives us sigma square I plus 1 minus alpha bar t minus 1 minus sigma square I, which ends up being 1 minus alpha bar t minus 1. So our q sigma of xt minus 1 given x0 ends up to be this. Now since we define the base case specifically such that q of xt is of this form, where t is the last time step, and then given q sigma of xt given x0, we have shown that q sigma of xt minus 1 given x0 is also of the same form. Hence, using this definition of mean function, q sigma of xt given x0 is always this for all time steps. Since our two conditions are met, that is, we have the mean of distribution as a linear combination of xt and x0, and we have shown that q of xt given x0 has the same form as DDPM, then a trained DDPM model can directly be used for sampling for these diffusion processes as well, even though here the forward process is no longer Markovian. For this diffusion process, unlike DDPM, q of xt given xt minus 1 and x0 is not equal to q of xt given xt minus 1. You cannot go from xt minus 1 latent image to xt without having knowledge about x0. To show that, we can use the Bayes theorem to compute q of xt given xt minus 1 and x0. Now here we have formulations for all distributions on the right hand side, all of which are Gaussian. And once we'll go through the process of getting the expression of q of xt given xt minus 1 and x0, we'll see that we can't get rid of x0 terms. Meaning, unlike DDPM, we can't say that q of xt given xt minus 1 is independent of x0. This mean formulation as a starting point might seem like magic. In our proof, we started from this expression and then showed that this satisfies all our conditions required for not training a model. But how did we arrive at this expression in the first place? Well, one way is that you start with your mean formulation as just a combination with some coefficients for xt and x0. That way you meet one of the conditions of reaching the same objective. Then we identify what values of these coefficients will ensure that q of xt given x0 will be this for all time steps, thereby meeting our second condition. Let's look at that also quickly. We'll assume to have q of xt given x0 of the same form as DDPM, and then using the same identity get q of xt minus 1 given x0. But we know that we wish to have q of xt minus 1 given x0 to also be this distribution. So we'll just match the mean and variances to ensure that they are same and see what coefficient values we ultimately end up with for AT and BT. These are now the values for all the terms involved in the identity. So according to the identity, mean of p of y or q of xt minus 1 given x0 becomes a mu plus b, which is this, and variance is this. But we desire the mean to be square root of alpha bar t minus 1 times x0, and variance to be 1 minus alpha bar t minus 1. So from matching variance, we get at as this, and then from mean and the value of at, we get bt as this. Now using these values, at times xt plus bt times x0 equals this mean formulation, which can be simplified a bit to match the same mean formulation that we have in the DDIM paper. So now this expression for mean doesn't seem like it came out of nowhere. Okay, let's summarize everything that we have done up till now. Rather than having a strict Markov definition of the forward process like in DDPM, which led to this objective, we have moved to a generalized non-Markovian diffusion process captured by these family of distributions indexed by sigma. So different sigma leads to different diffusion process. We have shown that this ends up to have the same training objective, at least if you ignore the weights for each time step. Regarding the weight term, we know that in DDPM, the authors ignored the weight factor to get a simplified training objective and ended up getting better sample quality with this choice. The authors of DDIM mention that if the parameters are not shared across time steps, like for example, say we have separate neural networks to denoise images for each time step, then we can completely ignore this weight term, because separately minimizing each of these terms by training individual models will achieve the global optimum anyway. So optimizing simple loss is same as optimizing the weighted terms of elbow, which means whether it's the DDPM objective or the objective using different coefficients, we can ignore the weights and thereby use the same simplified objective for optimizing both the cases, and hence use the same trained models. However, in reality, we don't use separate models. Instead, we have one model that iteratively trains for all time steps. But I'm guessing since we do additionally pass the time step information as input to the network, and if the model is powerful enough, ignoring these weights is okay. Great, so we have ensured that there isn't any change required in training. What about sampling? For sampling, we do need changes. For getting to the DDIM sampling equation, we first rewrite the ground truth denoising distribution's mean in terms of xt and noise. Since we know q of xt given x0 will always be of this form, we can rewrite x0 in terms of xt and original noise added, same as DDPM. And then in this mean formulation, replace x0 with this expression. From our ground truth denoising distribution, we get our predicted reverse distribution, which will have the same form, except instead of original noise, we'll have noise prediction made by our trained DDPM model, given xt as input. This gives us our sampling equation. So for DDIM sampling, we can use this update step. And similar to DDPM, we start with xt, a sample from normal distribution, feed xt to our model to get noise prediction, and then get sample for xt-1 using reparameterization trick. And then similarly for xt-2, xt-3, all the way till x0. Just for comparison, this was the update equation that we had for DDPM. A clear change that you can now see is sigma is also involved in mean formulation. Up till now, we haven't really talked about sigma at all. We have just said different sigmas will lead to different processes. But how exactly are those processes different? Let's take a look at that. Let's first start with sigma as 0. When sigma is 0, we can see that the entire process is deterministic. In the diffusion process, with same x0 and xt, you will end up with same x1 to xt-1 latents, because there is no variance at any time step. And if you look at the sampling process, with sigma being 0, the only randomness that is introduced is in the initial xt sample. But given same xt, we would end up getting the same set of xt-1, xt-2, all the way till x0 images every single time. This was not the case with DDPM, where the update rule always added a noise component at each reverse time step. So even with same xt, we ended up with getting different denoised images. As we increase sigma, the diffusion trajectory undergoes a change. For example, given a particular x0 from this simple distribution on the left hand side and a particular xt, we get this path from x0 to xt as a result of the diffusion process with sigma being 0. As we make sigma greater than 0, we start to introduce stochasticity, and with higher and higher values, the path is more stochastic. Of all the sigma values, there is a specific non-zero sigma value that is of special interest to us. That is this value of sigma square. This value is same as the variance used in DDPM's ground truth denoising distribution. Let's set sigma square specifically as this value in the update equation of DDIM and see what happens. Separating xt and epsilon theta terms and putting sigma square value gives us this expression, where the two alpha bar terms get cancelled out. Now what we have here is the same update expression as we had in DDPM sampling step. So in terms of the dynamics of the diffusion process, setting sigma equals 0 leads to zero stochasticity in the process, and as we increase sigma, we keep on making the trajectories more stochastic. And for a particular sigma, the dynamics of the process are same as DDPM. Moreover, with this specific variance value, our diffusion process now has q of xt given xt-1 and x0, same as q of xt given xt-1. So given xt-1, xt is independent of all other time steps, exactly like DDPM. To show this, we can take the ground truth denoising distribution, and then using Bayes' theorem, we can get q of xt given xt-1 and x0. Now we already know q of xt given x0 and q of xt-1 given x0, and it's same as DDPM. If you remember in DDPM video, we actually did the opposite. From q of xt given xt-1 and x0, we got the expression of q of xt-1 given xt and x0. Following similar method, we can get the distribution on the left hand side. Once we set this value of sigma square in the expression of q of xt given xt-1 and x0, we should have all the x0 terms vanish, allowing us to conclude this relationship for forward process when that specific value of variance is set. And you can anyways get a sense of that because we have seen setting variance to this value gives us the same ground truth denoising distribution as DDPM. So if all three distributions on the right hand side are same as DDPM, which means for this sigma value, the left hand side distribution q of xt given xt-1 and x0 should also be same as DDPM, which is just q of xt given xt-1. With our defined family of distributions, where the forward process need not be Markov, we have shown that there is no need to retrain models, and the only change is in the sampling algorithm. Now based on similar idea, we can also define diffusion processes where we don't go through all time steps and start skipping them. So that way, during reverse process also, we don't need to go through all 1000 time steps, which helps us reduce the inference time. And again, we don't need to worry about retraining the model as long as two things are taken care of. Q of xt given x0 is same as DDPM for all time steps, and mean of ground truth denoising distribution for the non-skipped steps. So q of xt minus I given xt and x0, where every time step from t to t minus I is skipped. This mean should be formulated in such a way that it ends up being a linear combination of xt and x0, or epsilon. The authors of DDIM introduce a slightly different factorization of the joint distribution for this part. The 1000 time steps are divided into two parts. all time steps that belong to a subsequence tau are those which are not skipped. The last time step in this subsequence, tau s, is going to be t, which is 1000 for DDPM. So these would be concerned with the following latents. And this part of the factorization deals with all these time steps that are not skipped. Then everything else, so all the time steps which are skipped, are dealt within this part of the factorization. Now according to this, how can we get the sequence of noisy images given a clean image? We first get xt or x tau s from x0. Then using x0 and x tau s, we get x tau s minus 1, the second last time step in the subsequence. Then x0 and x tau s minus 1 gives us x tau s minus 2 and so on. All the other latents that belong to the skip time steps are generated directly given x0. Similar as before, to ensure that even in this skip time step case, we don't need to retrain our models, the authors define the distributions in a specific manner. For all t that is skipped and the last time step, q of xt given x0 is defined explicitly to be same as DDPM. For all time step that is involved in the chain, so these time steps, q sigma of x tau I minus 1 given x tau I and x0 is defined as this. So same as before, except now instead of t minus 1, we have tau I minus 1, which gets us to the previous time step that is not skipped. The only thing that we need to additionally ensure to be able to use DDPM model itself is that q of xt given x0 should be same as DDPM for all time steps. To prove that for the non-skip time steps, the marginal distribution is indeed the same as before, we can use similar proof that we did using induction. The base case will be xt, where t is the last time step. And then if x tau I given x0 is this, we can show that x tau I minus 1 ends up to be the distribution of the same form by making use of the same identity from before. Only difference is now everything is in terms of tau I and tau I minus 1. The authors define the generative process where only the time steps that are not skipped are involved in the sampling process. Once we go through the process of getting the expression for elbow in the similar manner that we did for DDPM, we'll end up with similar KL divergence terms that we get in DDPM. We just have to work with all the terms involving time steps that are not skipped separately and all the terms involving time steps that are skipped separately. The authors show this in the appendix of the paper. For this scenario of skipping steps, the update equation is mostly similar to what we had before. For the case when a subsequence is used, the only change is that we go from x tau to x tau minus 1, and the alpha bar terms are also for tau and tau minus 1 time step. So if you are skipping 100 steps, then from 1000 time step, you'll go to 900, then to 800, and so on. A little implementation detail is how the subsequence of time steps are selected. For this, the authors consider two ways of selecting, linear and quadratic. In both cases, the constant value c is chosen such that the last term, that is tau s in the subsequence, is close to 1000 or the total time steps. So if we want to improve the sample generation time for a DDPM trained model without significantly affecting sample quality, all we need to do is change the update equation in the sampling part. Rather than this, which was our DDPM sampling step, we move to the DDIM sampling step. In terms of implementation, that is all that is required for DDIM. For intuition, I found it easier to think of there being only a smaller sequence of time steps, instead of all 1 to 1000. Since we have set the mean and ensured q of xt given x0 meets our requirement to reach same objective as DDPM, even if we had trained a model on this smaller length chain, we would have followed the same DDPM training process. It's just that rather than training a model for only these set of time steps, we instead have trained with extra set of time steps as well, by training our model for all 1000 steps. So just extra supervision. A thought might come that why not skip steps in DDPM during sampling time? The authors, in response to one of the reviewer's questions, specifically mention some points regarding this. DDPM sampling has a higher variance noise added at each step, so the stochasticity of the trajectory makes it harder for larger jumps. We could simply reduce the variance at sampling time in DDPM, but that will lead you to a poor approximation of the reverse process. With the reformulated mean of DDIM coming from a generalized non-Markovian process, we have changed the trajectory itself, making it completely deterministic for sigma equals 0, which allows us to make these large jumps. There is another SDE interpretation of it, which allows us to reach the same conclusion. That is, we don't need to retrain models and we can skip steps, but that requires talking about score and some other aspects as well. So I've covered that later in the video. For now, let's look at some results. Making the change to have only 50 steps in the subsequence leads to a much faster generation time on the DDPM model that we trained on MNIST. But obviously the sample quality will not be as high as DDPM. However, based on the results the authors provide, the quality degradation is not that significant, and when compared to DDPM with smaller steps, DDIM is much better. DDPM still gets the best result, but as we start skipping steps and work with smaller time steps, we get much better results from DDIM. Here this eta refers to the multiplicative factor present between DDPM and DDIM variance. So DDIM variance equals eta square times DDPM variance, which was this. Hence this result belongs to the deterministic case when sigma for DDIM is 0. And this case is same as DDPM. The sigma hat refers to the case where you have beta underscore t as the variance for the reverse process in DDPM. Before moving to other interpretations, there are a couple of interesting results in the paper which I want to briefly mention. One is that when working with deterministic case, we saw that generated x0 depends only on xt. But the authors also found that regardless of the number of steps used, the generated image given same xt but different number of steps has mostly similar high-level features, which means xt alone captures all the high-level details, and the length of trajectory affects the small finer details, as longer trajectory indeed generates better but semantically similar result. Second is that because for deterministic case, same xt leads to same image, and given that most high-level features are encoded in xt, when we interpolate between two xt's, we end up with generated images that are semantically meaningful interpolations between the denoised versions of the initial two xt's. Okay, so now we'll look at a different interpretation connecting DDPM and DDIM, and in process look at two other perspectives of diffusion models. While I don't go into details of both, however, I will try to give a high-level overview of the two perspectives, and through that also briefly touch upon some of the terms that you might see in papers. I have linked few videos in the description which go in significant details into these topics, so do take a look at them. For both perspectives, we need to have an idea about something called score. Given a probability density function, score is the gradient of log of density function. The gradient here is taken with respect to the input x. Effectively, what does this gradient represent? At all points, the gradient of log of p of x represents the direction in which one should move to increase the log likelihood most. Or in other words, the direction in which one should move to get to an x which is more likely. In terms of image space, if you are at a random point, it will give you a direction in which you should move to get to an image that is more likely to come from your image data distribution. So what can we do with this score? If we had this score available at all points, then you can generate samples from this distribution. We can just start with, say, k set of random initial points, and then simply move each of those k points a little bit in the direction of gradient. After repeating this for a large number of steps, we will end up with points that have very high likelihood according to the probability density that we are working with. But now all the points will ultimately collapse to this local maxima of likelihood. So we won't really be getting samples from all the regions of the density function. Which is why we instead follow the noisy gradient, where we also add some noise at every step, allowing us to generate samples from the underlying density without everything converging to local maxima. This, where you follow the gradient and add some noise, is Langevin dynamics, which you will often find reference to in diffusion papers. There is a specific value for the coefficient of gradient and noise, but let's just use this equation itself. So in theory, if we have a neural network which using samples of observed data or images in our training data is optimized using an objective like this, and here we are simply having our neural network predict a score which is close enough to the actual score, given a data point x or given an image in our training dataset. Optimizing this should allow us to have a model that enables us to generate samples. But the problem is that we don't have access to this score of p data. We only have access to samples from p data. So we need to do something about this term. It turns out that under certain assumptions, optimizing this objective is same as optimizing this one. Where now if you see, we don't have gradient of log of p data term. And the only thing present in the objective is score returned by our neural network for our data points. I've included one of the videos that goes through the entire proof of this in the description. So if you are interested, you can take a look at that. While this expression is something that we can work with, but here also the second term ends up to be computationally very expensive, especially as the dimension of data that we are working with increases. Then in one of the papers, the authors found connection between score matching with denoising autoencoders. The idea is that if we take our data points and add small amount of noise to get to a distribution q sigma over slightly noisy data points, then assuming the noise added is small enough, estimating the score of this perturbed distribution is close enough to estimating score of p data. The authors proved that optimizing this objective ends up to be same as optimizing this final objective. And here, we are just estimating the score of our noise function, the function which given an image x generates a slightly noisy version of it. If the noise that we have added is Gaussian, then the gradient of log of Gaussian will give us this term. But the numerator here is just noise that was added in x. After all, that's how we got the noise perturbed image. Take the original data or image and add noise to it. So this means learning to estimate score using available samples of p data or training data images is equivalent to taking a slightly noisy image and training the network to estimate the noise that was added. Now you can see that while the perspective that we had was entirely different from what we had seen in all the diffusion model videos, where we looked at the model as if it was a hierarchical VAE. But the objective that we ended up in an attempt to estimate the score is same as before, that is estimate the noise that was added. Which is why diffusion models can be seen as score-based models that use score matching for training. With this approach, there is still a problem. Your neural net rarely gets to see images from low-density regions. After all, since your training data would be samples from this distribution, most of those would correspond to higher likelihood regions, making the estimation by the trained neural network very poor for low-density areas. One of the ways to tackle this is that we don't just work with one noise level, but multiple noise levels. As we add more and more noise, we end up covering our entire space. And now we can run same Langevin sampling, but at each noise level. So we take the highest noise level, sample a bunch of random points, and after certain iterations of following the noisy gradient, we now end up with an output that can act as a good starting point for the next level of noise. And this process goes on for all the noise levels. And at the last noise level, which is the least amount of noise, after running Langevin sampling, we get samples that are similar to points from data distribution. This sampling approach that we went through is taken from noise conditional scored network. The neural network here gets the noise perturbed data as input as well as the noise level. By the way, this now looks very similar to our reverse diffusion, where we start with random noise, bit by bit remove noise, and ultimately reach a clean image, as if it was sampled from our original distribution. With this background on score, let's move to the second interpretation, which will also link back to DDIM. Up till now, we have been looking at diffusion as a discrete time process, where we take original data or x0 image and go to x1, x2, all the way till 1000 time steps. What if we interpret it as a continuous time process, which is what diffusion usually is, like diffusion of particles in fluid? So we can think of it as there being infinite number of time steps in between. Now this stochastic process, which takes our data distribution and at time t results in a normal distribution, this process can be modeled using stochastic differential equations, which have this form. We did look at such an equation very briefly in our DDPM video, where we just saw it as a change in x expressed in terms of a deterministic and random component. Just to add more details here, at every moment in time, we have xt, which is a random variable, and p of xt, which is a probability density describing the likelihood of xt taking different values. x0 is a random variable, the distribution of which is our data distribution, while xt is a random variable following standard Gaussian distribution. The SDE above describes how xt evolves over time, capturing the relationship between all the xt random variables in the stochastic process, and describing how xt changes with a small time step dt. If you look at our DDPM equation for the forward process, where we are transitioning from xt to xt plus 1, and if you express it as change in x, then after some approximations and under the limit of difference between consecutive time steps approaching 0, so basically to transition from discrete time to continuous time formulation, if we do that, then we'll get to this SDE. But more than the forward process, we are interested in the reverse process, because after all we want to generate data from noise. So in a paper of 1980s, it was shown that given this forward SDE for a stochastic process, then reverse of that, that is the process going back in time, can be described through this reverse SDE. Now going back to DDPM, from the forward SDE of DDPM and the general form of reverse SDE, we can get the reverse SDE for DDPM. Notice again the presence of our score function here. With the proper values for the drift coefficient, which is the coefficient of deterministic term, and diffusion coefficient, which is the coefficient of the random term, taking these from the forward SDE, once we discretize this reverse SDE with delta t as -1, since we are going from t to 0, then again with some approximation, we get an expression very similar to our DDPM sampling step. Just that instead of expressing in terms of score, DDPM sampling step has noise prediction in it. But if you compute the score for p of xt given x0 and rewrite x0 in terms of xt and noise prediction, you will get to similar expression as DDPM sampling step. So all this was concerned with DDPM. Now we are going to move to DDIM. Given this SDE for a stochastic process, there exists a deterministic process which has the same marginals as before. So at any time t, the marginal p of xt remains the same as the stochastic process. But p of xt given xt minus 1 differs, which means the transition and the trajectory also differs. This deterministic process can be modeled by the following ordinary differential equation. And just forget about the term. The only thing that you should focus on is the absence of noise that was there before. If you look at the DDIM step update, for the deterministic case, we have sigma as 0, and separating xt and noise prediction terms, we get to this update. Simplifying this, together with applying some approximations, and under the limit of beta t being close to 0, we can get to this update step, which is similar to what you would get by discretizing the reverse time ODE for the DDPM SDE from before. The main takeaway from this should be the deterministic nature of system and how this part of the update again refers to our score function. But because we have ensured that the marginals are same as that of SDE, we don't need to train the score estimator again. The same estimator trained on SDE, which means DDPM trained model for our case, can be used for the ODE, which is DDIM. In terms of trajectory, the change from SDE, which had this trajectory for the reverse time case, to ODE leads to our trajectory now being very smooth, which also provides us with the feasibility to skip time steps and make larger jumps in the reverse process, which was not possible for the non-smooth trajectory that we had for SDE or DDPM. The SDE interpretation, apart from allowing us to reach to the same conclusions but from a different perspective, it also enables us to start using a pool of solvers that exist for solving SDEs. We can just use different solvers for our SDE or ODE, and we'll end up with different sampling techniques, some of which allows us to achieve even faster and higher quality samples. That brings us to the end of everything that I wanted to cover for DDIM. I obviously did not go into much detail on score or even the SDE part. Hence, to understand them in depth, I would suggest to go through these 4 videos, which dive much deeper into score-based models and other aspects. The first one also has the proof of how we ended up eliminating the need of having score of p data. The second one goes into score-based models. The third talks about diffusion models from the perspective of hierarchical VAE. And fourth one talks about SDE perspective, sampling techniques, and few other topics. Hope this video was able to give you a better understanding of DDIM and also a peek into other perspectives, which will make digesting future papers you read a bit easier. Thank you so much for watching this one and your continuous support.